In the previous video, we construct some smooth cutoff function, and in this video, we will continue the proof of the Pancara type inequality, and finally, we will use this inequality to prove some rigidity results when the ambient domain omega is taken to be a Euclidean bore. And since we want to prove the Pancara type inequality by stability, we will have to compute the second variation formula for the free energy. And when M is a C2 hypersurface, such second variation formula has been computed by Xuwen Zhang. And since we are dealing with M, whose regular part of it is almost the same with M. So we can use the same result for the smooth case, and which is the following. For any admissible initial velocity, x, which satisfies that x is tangent to the boundary of omega, and the integration of x dot with nu m vanishes over m. And for such initial velocity, we have the second variation formula. And we skip the proof of this formula, and we refer to the Xuwen Zhang's paper for a more detailed account. And now we can start to prove the Pancara type inequality. Briefly speaking, if M is a capillary stable set of finite parameter whose singular part is closed and of a low Hausdorff dimension, which is at most n-3, we can have the following Pancara type inequality. And let's start to prove. First, we should construct some admissible variation. We fix a small constant epsilon, and we consider any smooth function theta defined on the regular part of M, satisfying that the integration of theta over M vanishes. Then we will use the cutoff function phi epsilon. First, we set this cutoff function, we set this smooth function theta tutor epsilon by theta times the smooth cutoff function. Then we modify this smooth function to have a new smooth function theta epsilon, which satisfies these properties. It is identically zero in the smaller region, and outside the bigger region, the new smooth cutoff function, the new smooth function theta epsilon is not far from the original choice theta, and theta epsilon converges to theta in the H1 sense as epsilon goes to 0. This is derived by the fact that the energy of the smooth cutoff function is small. It is bounded by some constant times epsilon. And the most important thing is this. For any choice of epsilon, we want that the integration of this new smooth function theta epsilon is integral over m vanishes. And that's why we have to smoothly modify this to have a new function theta epsilon, because we want that for any epsilon bigger than 0, the new smooth function theta epsilon has this integral. And moreover, we can smoothly extend theta epsilon to the whole Euclidean space Rn to satisfy that the directional derivative of theta epsilon along nu m vanishes on this set. And now we can use theta epsilon to define the admissible initial velocity, which is this combination. Here, for example, this is m, and nu gamma m is the unit conormal of m at the regular part of m, and nu m is the unit orthonormal of m at the regular part of m inside omega. And here, n epsilon is the smooth extension of the unit conormal to the whole m. For example, it should be like this. And nu m epsilon is the smooth extension of nu m to the whole m, which means for nu m, it is only well defined at the regular part of m. But now we smoothly extension it to be defined on the whole m, which also have definition at the singularity. And this constant is chose to satisfy that x epsilon is tangent to the boundary. And this is because we have m is a capitalist surface, a capitalist set of finite parameter with a constant contact angle theta with the boundary of partial omega. And here, this is due to this constant contact angle theta, which satisfies that cosine theta is minus beta. And moreover, we can check that this inner product indeed vanishes, which shows that this combination x epsilon is an admissible initial velocity, which doesn't preserve the volume in a short time, but preserve the volume at the first order. And now, recall that for this initial velocity, we smoothly modify it inside omega to be an indeed admissible set, which has the same volume with the original set, and this is the free energy of the admissible set, and this is the free energy by the initial velocity. And we have their relation. It is, and we take the second derivative to see this parameter hold. And for this integration, we can use the divergence theorem to give the mean curvature, and the boundary term vanishes because G epsilon is 0 at the boundary. And by definition of G epsilon, this is indeed this guy. And since E is a stable set, which means that the second derivative of the free energy among the admissible volume preserving variation is non-negative. So we have this formula, this inequality. And then we can use the second variation we just talked about to see this formula, to see this inequality holds. Here M is this inner product. Then we can let epsilon goes to 0 to see that the Pancara type inequality holds. Indeed, we can check that for this F, it coincides with the theta epsilon on the regular part of M. Then we can plug in theta epsilon to this inequality to see this formula, to see this inequality for theta epsilon. And here we have the second order term, and we can use the divergence theorem to have only the zero term and the first order term, and use the fact that theta epsilon converges to theta in H1 sense, and finally we can let epsilon goes to 0 and use this convergence to see that the Pancara type inequality holds for any smooth function theta whose integral vanishes over M. So we have the Pancara type inequality, and we will use it to prove some rigidity results. And our motivation is that such result holds when M is a C2 capillary stable set, and a C2 capillary hypersurface in the Euclidean bore. And this result was first derived by Wang and Xia in 2019. And since our choice of M, since our M is a capillary stable set of finite parameter, whose singular set is of a low Hausdorff dimension. So we can follow the same proof when M is a C2 hypersurface to see that the regular part of M is umbilical, which means that it is either a totally geodesic bore or spherical cap in Rn. And for the singular part, we will rule out them by the stability. First, for the regular part, we consider this conformal killing vector field. And a good point for this vector field is that it is tangent to the unit sphere in Rn. And moreover, when M is a C2 hypersurface with a constant contact angle theta with the Euclidean bore, we have this Minkowski type formula. Which means that for the regular part of M, we also have this formula because we can view the regular part of M as a C2 hypersurface. So in order to use the Pancara type inequality, we will have to construct some smooth test function, which is smooth on the regular part of M and with its integral over M vanishes. And we define this test function to be this guy. And we can check that it is indeed, its integral is indeed 0. So we can use the Pancara type inequality to see this formula hold, to see this inequality holds. And here, if H is 0 and theta is half of pi, which is the free boundary, which is the free boundary case, then we can see that this guy vanishes and this guy vanishes. This guy vanishes. So the integration of this times this is non-negative, is non-positive. And since this is non-positive or non-negative, we can see that this guy must be 0. And the second fundamental forms norm square of M is the sum of the principal curvature of it, which shows that M is a totally geodesic bore in Rn, so it is a hyperplane in Rn. But now, if h and theta doesn't satisfy this formula, we will have to consider this following function, phi, defined by this formula, and a direct computation will give us the tangential Laplacian of phi is this guy. And by this and this formula, we can have this inequality. And by some direct computation, we will finally arrive at this integral is bounded bounded above by 0 and bounded below by 0. So it is indeed 0. And here, by Cauchy's inequality, this guy is non-negative. And so this integration is 0, means that this term and this term must be both 0. Then we can then we can compute and to see that this formula holds on any regular point of M, which shows that this guy must be 0 on the regular part of M. And again, by Cauchy's inequality, we have this guy must be bigger than or equal to this guy. And the equality holds if and only if the principal curvature of M are the same thing, which means that the regular part of M is umbilical in the Euclidean bore. So the only thing left to do is the singularity analysis. And briefly speaking, we can construct some volume preserving perturbation which decrease the parameter strictly. And this will contradict with the fact that such M or such E is a local minimizer. And precisely, if there exists some singularity X here, then near X we can find some regular part, and we can use a bore with radius r, the same radius, to intersect this bore, and we will have this portion, the intersection of them. And we remove this part, and we add the same volume with this part to the singularity. And we will see that here, this parameter is the same with the original parameter, because these two bore out of the same radius, so the parameter of this guy must be the same with this guy. But here, near the singularity, the original parameter must be bigger than the new parameter, because when this is a plane, we can see this by a triangular inequality. So this means that we have some volume preserving perturbation, but decrease the parameter strictly. And the contradiction shows that no such singularity will exist. And which means that we rule out, we have some regularity by the stability of E. Here is the reference of this slide, and I want to thank you for your attention.